Um, Hello and welcome. My name is Diego Pelayo, and I'm going to be presenting my argumentative oral exam about the about modeling and electrical systems in bioengineering and chemical processes. So the main purpose of this whole presentation is, for this oral exam, um, I will explain the topics that were basically seen on class during the whole period, and I am about to try to explain them in the clearest way. And this explanation will also lead me to a better explanation of the challenge in the end, because all of these topics that we saw were used for this challenge. And yeah, so first I would like to start with electrostatics. So basically, electrostatics is the study of the electric charges at rest, and overall in physics it is encountered in many types of forces like gravity, friction, tension, and yeah. So but most of these are actually manifestations or fields of electromagnetic fields that exist um, in like we exist without us being able to see them. And well, electrostatic forces are specifically on how charged particles interact when they are not moving or moving very slowly. So I would like to start with what's a charge, which is like the most basic concept we can know. And well, overall, everything we know is made of atoms, and atoms contain protons, neutrons, and electrons, each of them with a positive or negative charge, which protons have a positive charge and electrons have negative charges, and neutrons have no charge, so they're neutral, I guess. And well, something important to highlight is how the most objects are electrically neutral, because they have equal number of protons and electrons. So most of these forces or charges cancel out. And yeah, so one of the main topics that we had to understand about electrostatics was Coulomb's law. So Coulomb's law gives us a mathematical way to calculate forces between charges. So this law states that the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. So that's what we can see in this equation right here. Also, we know that Coulomb is this is the definition of this equation, and this overall means that if the charges increase, the force will also increase, and if the distance increases, the force will become weaker very quickly. And a way to interpret this law is that it's similar to gravity, because they both follow this like inverse square relationship. However, gravity is always attractive, but electrostatic force can be either attractive or repulsive depending on the charges. As we know, negative charges will try to do like the opposite of the positive ones, The positive charges will always try to push, while the negative ones will try to attract. And yeah, so even though the electrostatic forces are very strong and we can calculate them as if they were real big numbers, we don't really notice them in like a daily basis, because most objects are electrically neutral, as I already mentioned, and so these charges just cancel out. So yeah, that's basically a part of what electrostatics is and Coulomb's law. And so for the next topic, I would like to present the electric fields. Let me just move here. So a field is the strength and direction of something, independent of whether it has an interaction with other bodies or not. Normally, when there's an interaction between charges, this is known as an electric force, which is basically a push or a pull. However, electric fields have no relationship with this kind of interactions, and so this can be known, the electric fields, as the source for electric forces to exist. And this is well, represented by this formula. And so electric fields are known to be vectors surrounding charges, particles, that exert forces onto other charges within its range. And we can see that these are the this is how they are represented, and this is also another equation that, as we mentioned before, with the r squared, they are proportional to whether it increases or decreases. And anyway, a way to describe electric fields overall is how charge an object affects the space around it. Instead of thinking that charges only interact with when they touch, we say that every charge creates its own electric field around it, and any other charge placed in that field will experience a force. So to define it, as I already mentioned with a formula, it can be that the electric field is the force per unit charge, which this tells us how much force in a small test charge would feel at a certain point in space. So something quite important to mention about electric fields is that they have both magnitude and direction. So they are represented as vector quantities, and the direction of the field is defined as the direction that a positive test charge would move if placed in that same field. So we often represent the electric fields using field lines, and these lines help us visualize like overall the field, and how, like, whether they point like outside, like they were pushing, or they were pulling something. That's gonna represent either if they're positive or negative. And also, the closer these lines are together between each other, it means that the field is stronger in that specific region. So another idea is that electric fields can become weaker as you move farther away from the charge creating them, and this is because the influence of the charge spreads out over space, reducing its strength with distance. So overall, electric fields help us understand how charges interact through space, but not specifically by a direct contact, but through the invisible influence that surrounds them. And for the next topic, we have the Gauss law. And so I think this is very important to understand because it's a whole concept that personally it took a lot of time to get a hold of. And so one of the other concepts we had to understand alongside with what Gauss's laws were was electric flux. And you can think of it as counting how many electric field lines go through a certain surface. And yeah, so and the more field lines that they cross the surface, the greater is the flux. And so this was like a basic concept to get to understand what Gauss law were. And so this law states that the total electric flux through a closed surface, that's why in the integral sign we have a circle, that means a closed surface. So the total electric flux through a closed surface is equal to the charge enclosed divided by a constant called the permittivity of free space. So that's what we can see in that equation. And one of the most important concepts that I consider for this law is that the charge inside the surface matters. Even if there are charges outside of the surface, they do not affect the total flux. So what this basically means is that Gauss' law depends only on the enclosed charge and not on the shape of the surface or external charges. So one key idea overall is that the field lines behave like they originate from positive charges and end up in negative charges. So if a surface encloses a positive charge, more field lines leave the surface that enter it. So this allows for a positive flux to result. And if there's a negative charge enclosed, more lines enter, giving a negative flux. Overall, this law is especially useful when there's symmetry. For example, in a sphere or a cylinder, or even in just a plane. These cases, the electric field is the same over the whole surface, which makes the calculations way simpler than if it was an irregular surface. And the methods that we were taught was to first analyze and choose a Gaussian surface, then use the symmetry to simplify the field, then calculate the flux and solve for the electric field. So that's basically what I overall understood of Gauss' law. Yeah, so this was also about the electric flux, representing how much electric field passes through a surface, and it depends about the magnitude and direction of the field. So that is basically what I already said. And next up, I have the electric potential. So first, I would like to define what potential is. And potential is potential energy per unit charge, which is this formula right here. And we can define potential that it's V as any point in an electric field as the potential energy, U per unit charge associated with the test charge Q0 at that specific point. So what overall electric potential is defined as electric potential energy per unit charge, as already mentioned. So this tells us how much energy a charge would have in a specific point in an electric field. Yeah, I just repeated that, but okay. So something that it's a helpful way to understand electric potential is to think of it like height in a gravitational field, just like an object at a higher position that has more gravitational potential energy. A charge in a region of higher electric potential has more electric potential energy. Also, something that it's included in this topic is the potential difference. That in practice we are usually interested in the difference in electric potential between 2 points, which this is known as voltage. This represents the work needed to move a unit charge from one point to another in an electric field. So the electric potential can be related um, to work and energy. So when a charge moves through a potential difference, its potential energy changes, and if the electric field does the work, the charge usually moves from higher potential to lower potential, releasing energy. And an example I kind of understood through all of this was that for a point, the electric potential decreases um, as the distance from the charges increases, and this shows that the influence of the charge becomes weaker as you move further away. So for the next topic, there are capacitors. So the capacitors stores energy by separating charges. Its capacitance is defined as charge over voltage. I think I did not, yeah, I didn't add an equation for this, but so yeah, the energy stored in a capacitor depends on both the capacitance and the voltage, which explains how devices like flash systems can release energy very quickly, as we saw that. Well, we're gonna see that later on for the challenge. And so the structure of a capacitor is made of two conductive plates separated by an insulating material called dielectric. And this dielectric prevents charges from moving directly between the plates while still allowing energy to be stored in an electric field between them. So basically, how does capacitor works? When a capacitor is connected to a battery, electrons move from one place to another, usually clockwise. No, not usually. It moves clockwise, and as a result, one plate becomes negatively charged and the other becomes positively charged. I like to think about it as an elevator that is going from the lowest floor to the highest floor. um, and because of the insulating material, the charges cannot recombine, so they remain separated at all times. And this separation creates an electric field between the plates. That is where energy is stored. So the energy storage, it's a concept that I understood up until this topic of capacitors. And the important idea is that capacitors not only store energy like a battery chemically, but it instead stores energy in an electric field created between these plates, as I already mentioned. And the greater the charge separation, the greater the stored energy. So one concept that is also important to understand in capacitors is capacitance. That is the ability of a capacitor to store charge, and a large capacitance means that the capacitor can store more charge at a given voltage. The capacitance depends on three main factors. That is the area of the plates, the distance between them, and the material used as the dielectric. So another thing that is important to understand, and that we saw it through our challenge, is the discharging process. And when the capacitor is connected to a circuit, the stored energy is released. So electrons flow from the negative plate to the through all the circuit to the positive plate in a clockwise sense until the charges equalize. And this process allows capacitor to deliver the energy very quickly, which is why they are used in devices like the ones that we were testing. That was like electronic flash systems. And the applications in a daily basis in the real world for capacitors is, for example, establishing voltage in power supplies, smoothing electrical signals, providing quick burst of energy, which is our main goal for the challenge, and supporting devices during rapid on-off cycles. So later we have, for the last topic, current, resistance, and DC circuits. And a current, starting off with that concept, is any motion or of charge from one region to another, and it is defined as I equals the is Q over T, which is also like the flow of electric charge through a conductor, and it is measured in amperes, where 1 ampere is corresponds to 1 coulomb of charge passing per second. So in simpler terms, current represents how many charges are moving through a wire over time. And in most circuits, electrons are the moving charges, although we describe current as flowing from the positive to the negative terminal. And the next concept is resistance, which it opposes this flow of a current. And their relationship is given by the Ohm's law, which states that voltage equals current times resistance. So this is a concept and an equation that we already know from before. And so also resistance is the property of a material that opposes the flow, as already mentioned, from the electric current. And it determines how difficult it is for charges to move through a conductor. If the resistance increases, the current decreases because the material makes it harder for the charges to flow. And this relationship is described by Ohm's law, as already mentioned, which states that the voltage equals the current of resistance. And so an important concept to understand through all of this, the resistance, is the Ohm's law, that in a circuit, with the equation that we have here, it means that if voltage increases, the current also increases, and if the resistance increases, the current will also decrease. And this equation is fundamental because it allows us to predict how a circuit will behave regarding all of the elements that is inside of a circuit. So the next concept would be the DC circuit. So DC circuits is a circuit which current flows in only one direction and is typically provided by a battery. Unlike alternating current, where the direction changes, direct current remains constant, and this makes these circuits easier to analyze and very common in electronic devices. So in this type of circuits, we have two different ones, that is parallel and on series. Series circuits, in all of the series circuits, the components are connected by one single path, so the current has only one path to follow. And this leads basically to the current is the same through all of the components, and the total resistance is the sum of all the individual resistances, and the voltage is divided across each component. So that's one way of having these circuits. And in parallel, it's not the opposite but different, because they are, as the name mentions it, they're not exactly in one single path. They have different paths, and they separate the charges, and the resistances are, it was divided by the amount of resistors they are over the resistances that each one of the resistors has. And so in a DC circuit, the battery provides voltage, which gives energy to charges and causes current to flow. The amount of current depends on the resistance in the circuit, and this interaction is described by Ohm's law, and so the voltage drives the current, while resistance limits it, and together they determine the behavior of an entire circuit. So also another thing that it's important to mention is that DC circuits, when we are trying to calculate them, we apply Kirchhoff's law. That is, the sum of voltages around a loop is 0, which reflects energy conservation, and the sum of currents at a junction is 0, which reflects charge of conservation. And so lastly, we have our challenge, which basically was electrical light system, that we were aiming for it to make a burst of light in the fastest way possible, minimizing the delay. And so through the challenge, we were able to examine how energy is stored and rapidly released in an electronic flash system, using all the key electronic concepts that we already mentioned. And so we were able to first understand all of these concepts and get all of the equations that we needed, and also understand them and what each one of the components that we needed could work for these equations, and how the equations would lead us to get to the goal of this whole challenge. And also through we got to understand first how we could use these equations throughout of the semester, and then we just simply were given like the parameters and the terms that we were supposed to use. And for example, we got to understand that that parallel capacitors were helpful through all of these, because storing the results showed that a capacitor storing 4 joules of energy can discharge in a very short time under specific conditions, and this demonstrated how the interaction between capacitance and resistance control the speed of energy released in a circuit. We also got to understand how to manipulate the data we were given in order for us to get to the result. And so yeah, that's basically what we did for this project, and how we developed it. So yeah, for the last part, I was I was mentioning the challenge, and so here is like the whole challenge, with which we have separated by the sections that were supposed to be. And so here we have all the theory explaining each one of the concepts that we needed to understand in order for the whole experiment to be created. So here is the whole part of the results, which here we can see that we have the parameters and the data that we were given by our professor, and here is how we start to use this data and the formulas that we already know in our favor to get to the result. And so starting off, we have here that with the voltage that we were given and the resistance, we get that the power that was given is 625 watts. However, we were specified that the minimum power that was needed was 1300 watts and a maximum of 2500 watts for at the both terminals for the whole system to work and the flashlight to be as strong as it needed to be. That was like the maximum it could be. And so here we know that yes, knowing that the 1300 watts was the minimum, we could just not use directly this power. So we have to understand how the capacitors could work, and using the Ohm's law that we already know, we took a closer look to how the different methods of the capacitors could work, and so we came to the conclusion that this type of capacitor was the best one, since we could just sum all of the resistance together and we got a higher number. And so we then got to use this formula that we needed to get the energy stored in a capacitor. And so we just replace the values that we already know, that is the power that we were given here and the voltage that we already knew, resulting in the 4 joules that we already mentioned before. And so knowing this, we only need to find the relationship between the time, so we can know how much time we could decrease with this data already to get to the goal of the challenge, that was basically to create the flashlight, minimizing the time, the delay. So we know that these 3 formulas are the ones that we need, and so we just start changing the values of each one of them. As we see here, we know that delta V is delta V to the current times the current times e to time over RC equal. So we just start changing all of these values in order for our final equation that we could use. And so as we already know that power of time is equal to du dt, we just substitute these values over each one of the corresponding ones, and we get to the equation that says power of t equals to delta v I squared over the resistance times e to the minus 2 times time over RC equal. And so we just substitute the values we already know. And well, this is just pure algebra to solve the equation, and we get to 0.00078 seconds, which is somewhat what we were expecting. And this is a graphical representation of this same formula, getting a straight line and with the exact point of the 1300 watts that we needed. And so yeah, that's basically the part of the results that we got from this whole experiment.